Today, we are actually going to look at cubic functions. By the end of the lesson, you should understand that a cubic function is a polynomial of degree 3. You should know how to identify a cubic function using a third order difference. You should be able to recognize a cubic function in general form and identify the critical features of a curve. And finally, be able to determine the domain and range of a cubic function. Now, let's have a look at cubic functions. We know the general form of polynomial. For example, a cubic is 4x cubed plus 3x squared plus 5x minus 1. And a quadratic is something like a y equals 7x squared minus 8x plus 1. So, for both of them, you can see that cubic, the highest degree of the polynomial is a cube, and quadratic, the highest degree of a polynomial is square. And we know that the cubic function or relationship has the general form of y equals to ax cubed plus bx squared plus cx plus d. Remember when I show you in quadratic function how you could determine whether a function is quadratic or linear based on the order of difference. The same procedure applies for cubic function as well. Work out the first, second, and the third order of difference. As soon as the third order difference is actually a constant, or you have a third common difference, the function is actually a cubic function. And we should know the general form of a cubic function is y equals to ax cubed plus bx squared plus cx plus d. Now, I would like you to pause the video for a while. Use this table of value, see if you can determine if the relationship between x and y is a cubic relationship. Now, check your answer against mine. I've worked out that the third order difference is actually a constant, which is 12. Therefore, it is actually a cubic function. Again, I would like you to pause the video for a while and work on this. Determine if this is a cubic function. Right, this is my answer. And you can see that I've worked this one out as a cubic function because the third order difference is actually the same and is constant. Right, I'm using the same tree graph again, and this time you can see that I have got the maximum and minimum turning point for all three graphs. In the first one over here, it looks as if there's very little difference between the maximum and minimum turning point, but if you actually enlarge the scale, you should see that there is actually a difference. Here is more prominent, so with the third one, it's actually a lot more prominent. In the second one here, you can see that the minimum turning point is actually the x-intercept. This one here, the third one, the maximum turning point is not actually at the y-intercept. I am actually going to show you how to use your class pad to determine the maximum and minimum turning point. So please get your class pad out. We are going to learn how to determine the range of a cubic function. So now let's have a look at y equals x cubed. Here I have drawn y equals to x cubed and enlarge the scale in terms of the domain that we are looking at, -5 to less than -5. Now, I would like you to note that in the case of y equals to x cubed, there is actually no minimum turning point or maximum turning point. All right, so here it approaches 0 and then it just changed to from negative and it changed to positive. I'll talk a little bit more about that point a little bit later. But first, let's have a look at the range of y if dx is in the range of is in the real numbers. So you can see that there's no restriction. So for part A, the range of y or range of fx is y such that y is an element of the real number. Now part B, let's have a look. Part B, we are looking at from -5 to +5. So we're going to include this point here and this point here as the range. So we know that when x is -5, y is -5 cubed, which is -125. And when x is equals to 5, y is equals to +125. Therefore, the range of y in this case is y is actually an element of the real number and is from -125 to 125. Alright, let's pause the video for a while and I would like you to work on C and D actually. So for C, we are looking at less than 0, the domain of less than 0. So you know that when x equals to 0, y is equal to 0. Therefore, the range of y is actually y is such that y is a member of the real number and y is less than or equal to 0. And for part D, we are actually looking at between 0 and -4, this domain. So here we know that when x equals to -4, y equals to -64. Therefore, the range of y is such that y is a member of real numbers and is from -64 to 0. Right, the next one, I'm going to involve some maximum and minimum. Right, now for part A, it's very obvious. The range of y is actually y is such that y is a member of the real number or an element of the real number. That's all. There's no restriction at all. The next one, part B. We know that we are looking at the domain from 0 to 2. Alright, this time we know when x equals to 0, y is actually 8, which is the y-intercept. And then when x equals to 2, y is actually equal to 0. Now, the thing is, we know that when we use the class pad, there is a maximum turning point and the value is 0.214 and 8.209. And in fact, 8.209 is larger than 8. Therefore, this time, the range of y is actually y such that y is an element of the real number and y is greater than or less than 0 and less than or equal to 8.209. Alright, so we have to look at whether there's a maximum in that domain that we're looking for. So we know that the maximum falls within that domain, therefore the range is actually from 0 to the maximum. Now what about part C? Pause the video for a while and see if you can work it out. For part C, you know that it's from 1 and less than 1. So again, we can see that when x is 1, y is actually equals to 1 minus 5 plus 2 plus 8, which is 6. So therefore, it is actually less than the maximum turning point value, which is 8.206. So in this case, the range of y is such that y is a member of the real number, and y is actually just less than equals to 8.209. So anything below that fits in the domain. Alright, and then finally for D. So you are looking at between 2 and 4, that range. You know that when x equals to 0, x equals to 2, y equals to 0. And when x equals to 4, y equals to 0. However, you know that there is a curve, and that actually is a minimum turning point. And previously, from your calculator, you know that this is 3.120, and that is minus 4.061. Alright, let me write it better, minus 4.061. Therefore, we know that the range of y is such that y is an element of real number, and this time is minus 4.061. Y is greater or equals to minus 4.061 and less than equals to 0. So this is how you determine the range of a cubic function. You need to know approximately, you need to know whether a minimum or maximum occurs within that domain. Now, we are going to look at point of inflection. This is the point where the curve changed from being concave down to concave up, or from concave up to concave down. So you remember, concave down looks something like this. Concave up looks something like this. Alright, so here the point of inflection is somewhere here for the first graph, because this bit here is a concave down. And from here onwards, there's a concave up. Here, the second one, the point is here, and from here up to that point is actually concave down, and from here onwards is actually concave up. Alright, now let's look at what I call a horizontal point of inflection. Here, this is y equals to x cubed, and this is y equals to minus x cubed. You can see that there's no minimum turning point or maximum turning point. Same with here, the y equals to minus x cubed. There's no maximum or minimum turning point. Therefore, the point of inflection is called a horizontal point of inflection. Right, we're going to look at rotational symmetry. You can see that the red line here is actually the black line being rotated about the point A. So here, this is what you call a rotational symmetry. A function is said to have a rotational symmetry of theta degrees about the point xy if the point xy can be fixed as a pivot point, and the function can be rotated theta degree and returned to its original function. So here you can say that this cubic is actually has a rotational symmetry of 360 degrees at point A. Now, we have completed the lesson, and you should understand that a cubic relationship is a polynomial of degree 3